Welcome to the House of Shedo, a place for very interesting videos on physics and mathematics. Please subscribe. So today we'll be looking at simple harmonic motion. Now, this is one of the most interesting types of motion in physics. Now, remember back then in your elementary physics, you were taught the concept of motion, and then we were told that motion simply means the change in the position of an object or a body with respect to what? To time. And one of those types of motion being studied then was the periodic what? Motion. Now, physicists have discovered that the periodic motion is very fundamental in nature. There are different systems that their behavior is in the pattern of the periodic motion. When you look at the motion of the earth around the sun, it is periodic. The motion of electron at the atomic scale at the orbit is also what? Periodic. What is periodic motion? Periodic motion simply means the motion of an object in a repetitive manner at certain interval of time. So when a system repeats its motion at certain fixed time, we call that particular motion the periodic motion. So the to picture this, we can look at the motion of the earth revolving around the sun. The earth actually revolves around the sun 365 days to make a complete revolution around the sun. So that is actually periodic motion. So simple harmonic motion, which is our interest for this video, is actually a class of the periodic what? Motion. So what exactly is a simple harmonic motion? So what do we mean by simple harmonic motion? Now, one of the important way to actually characterize and make sense of what a simple harmonic motion actually is to look at the property that is actually fundamental to a simple harmonic motion system, and that property is the restoring force of a simple harmonic motion system. So what we have in this video as our illustration basically is the mass spring system, and when you look at the image, you see that the block of mass is actually moving forward from the equilibrium position and undergoing a displacement x. Now the force, the restoring force, is actually pointing backward, meaning that the restoring force is to restore the block of mass back to the equilibrium what? Position. So it is more like a through and fro movement, whereby the restoring force is always bringing back the block of mass to its equilibrium what? Position. So that is the idea of a simple harmonic motion, the kind of motion whereby the restoring force is directly proportional to the displacement of the motion in opposite direction, which simply means that the direction of the restoring force is opposite to the actual displacement of the system. So that is how to characterize a simple harmonic motion. And from the nature of the restoring force, which typifies a simple harmonic motion, it is easy to begin to derive other physical quantities that actually defines a simple harmonic what? Motion. But before we go into looking at other important quantities that defines a simple harmonic motion, let's consider examples of a simple harmonic motion. There are various examples of a simple harmonic motion we can consider. One of the examples is the motion of a simple pendulum. Another example is the motion of a vibrating mass attached to a vertical spring, which is part of the mass spring system, although we are actually using the case whereby the spring and the mass is actually in a horizontal format. We have the vibration of the eardrum is actually simple harmonic. We also have the vibration, the electrons in a wire that is carrying the alternating current is also simple harmonic. And of course, if you have ever seen a child swinging, during those elementary school days, you know that that is also a simple harmonic motion. Now, to begin to analyze a simple harmonic motion in order to know the form of the important quantities that defines the motion, we need to return back to an important law in classical physics, which is the second law of motion, the Newtonian law. Remember, the law states that the net force, whenever there is a net force on a system or an object, there will always be a rate of change of the momentum of that particular object. So the net force is always directly proportional to the rate of change of the momentum of that particular object. So basically, one of the importance of the Newtonian second law is, if we actually know the form of the force affecting a system, it is possible for us to actually calculate the displacement of the system. And once we know the displacement of the system, which is actually the path the system is going to follow, the trajectory of the system, then we can get the other quantities, which is velocity and acceleration. These are important quantities when analyzing a mechanical system. So if we actually take the restoring force, which is minus ks, where the k is actually representing the force constant, and the which is the spring constant, and the x is actually the displacement. If we take that form and substitute into the Newtonian equation and solve the resulting differential equation, we are going to get a displacement for a simple harmonic system, especially for the mass spring system that we are focusing on. We are going to get the displacement as a cosine function. Actually, the general form of that displacement is have both the sine part and the cosine part, but we can rewrite that in terms of only the cosine function. So the displacement is the amplitude times cos wt minus phi. The w is actually a constant, which is the angular frequency, and the phi is actually representing the phase of the system in motion. So this is the displacement, and mathematically we are using a cos function as a solution to the differential equation, because the cos function actually satisfy the differential equation. And this is significant because it tells us that the cosine function is able to actually model a simple harmonic motion. So is actually an oscillatory motion. So the cosine function is actually a good mathematical model for such a trajectory. So from the displacement of the motion, we can get the velocity. Velocity is the rate of change of displacement with time. So when we make that differentiation, we get the velocity as minus aw sine wt minus what? Minus phi. And using trigonometric identity, we can rewrite our velocity in terms of the displacement as W square root of amplitude square minus displacement square, and the maximum velocity, which is a constant, will be the amplitude, the product of the angular frequency and the amplitude. And then we can get the acceleration by differentiating with the velocity with time, the rate of change of velocity with time. So we can get the acceleration as minus a w squared cos wt minus what? Phi. And if we make a substitution, remember the expression for our displacement in terms of the cosine function, if we make that substitution, we'll get the acceleration as minus w squared x, which is actually one of the fundamental equation that actually characterize a simple oscillator system, which tells us that the acceleration is directly proportional to displacement of the system and in opposite direction, and the maximum acceleration is gotten as a w squared. Now if we actually check at the constants that we can find in the simple oscillator system, we'll discover that one of the constants, which is the spring constant, which is k, and then we have the mass. For our model, the mass is representing the mass of the block, and then we have the angular frequency. So they are related by this expression that the angular frequency is square is equals to k over what? M. If we use the relation between the angular frequency and linear frequency, which is angular frequency is 2 pi f, we're able to get the linear frequency of 1 over 2 pi square root of k over m. And when we use the relation between period and linear frequency, which is period is the inverse of linear frequency, we should be able to get our period as 2 pi square root of mass over k. So those are the quantities that actually define the simple harmonic motion. And it is important to state that we decided to also include the expression for the period because remember we say that simple harmonic motion is a class of the periodic what? Motion. And when we talk about periodic phenomena, it is important that we mathematically define the form of the period for that particular what? System. And because we are dealing with oscillation, it is important we also talk about frequency, which is why we are given the expression for the frequency of the motion. Now it is also important that when you are dealing with a mechanical system, it's important that you also want to know what will be the form of the mechanical energy, and most importantly from the perspective of conservation law, to know whether within the system whether the total mechanical energy of the system is actually what? Conserved. Remember, it is an important and a universal law for mechanical system, the law of conservation of mechanical energy, which made us understand that though the kinetic energy and the potential energy of a system can vary from point to point, but the total mechanical energy, which is the sum of the kinetic and the potential energy, must always remain what? Constant. So if we derive the expression for the kinetic energy of a simple harmonic motion, which is a mass spring system, starting with the general form of kinetic energy, which is half mv squared, and making an appropriate substitution, we should be able to have the kinetic energy as half ka squared sine squared wt minus phi, which we can recast in the form whereby we have the displacement inclusive, and the potential energy can be written as half ka squared cos square wt minus phi, which we can put as half kx squared. This interesting. This is actually telling us that the potential energy of the mass spring system is actually the elastic potential energy, because it's depending on the elastic spring constant, which is what? Which is K. So if we sum, based on the expression on the screen, if you sum the kinetic energy, the last form of the kinetic energy and the last form of the potential energy, in order to get the total mechanical energy, we'll discover that the total expression gives us half K A square, which is quite interesting, telling us that half is a constant, K is a constant, A, which is the amplitude of the motion, is the system, is also a constant. So this tells us that the total mechanical energy of the system is actually a constant. So it tells us that the system actually obeys the law of conservation of mechanical energy. The form of the kinetic and the potential energy actually satisfy that particular conservation principle, and which is actually expected because we are dealing with a physical system. If we are not able to get a mathematical expression for the total mechanical energy to be constant, then then there is problem somewhere, because we are dealing with a mechanical physical system that should obey the conservation laws of physics. So those are the equations that actually govern a simple harmonic system. The mass spring system we are using in this particular video as our model system. So let's quickly look at problem solving. The first problem here, we are given a mass that performs. Now we are told that the phenomenon here is the simple harmonic motion. So that tells us that we are going to solve this problem using the equations of simple harmonic motion. Actually, the idea of problem solving in physics is to look at the problem and identify what actually is the phenomenon, what actually is the system, is the particle, and what actually is the phenomenon in that particular problem, because the laws of physics must be in line with the phenomenon and the system of the problem. So the phenomenon here is a simple harmonic motion, which is a simple harmonic system. So we are going to apply the equations for the simple harmonic motion in order to have an organized logical solution and thinking. It is good we organize our information. So you can see the information, putting them in appropriate units, converting gram to kilogram, converting centimeter to meter. Now the first thing to calculate is the maximum displacement from the mean position, which is actually the amplitude. So in calculating the amplitude, we use this form of the expression of the velocity. We have the velocity already. We don't have the angular frequency. We can rewrite it as 2 pi f. We have f already, so we can use it, and we have the displacement already. So when we make all those substitution, we get our a as 0.12 meter, and then we get our maximum velocity using the maximum velocity expression, which is wa. We're casting it as 2 pi fa. We get our maximum velocity as 3.77 meter per second, and then the maximum potential energy. Of course, the potential energy is half kx squared, but because the answer of the maximum potential energy, we need to interchange the expression x for a, which is actually the maximum displacement. And because we don't have k is not given, we can recast the equation to a form that the quantities are available. So we can write it as m half m 2 pi f all square a square, and make our substitution. We have our potential energy to be 1.42 times 10 to the power -1 joules. And on a final note here, we have another problem, an oscillator with a period of 2.4 meter per second. Now the point here is that the system we are dealing with is an oscillator system, which is a simple harmonic motion. So the question is for us to find the equation of the oscillator motion. Of course, the equation of motion of a system is actually the displacement of that particular system, because the displacement is the first expression that you get from the Newtonian, from solving the Newtonian law before you get the velocity and the acceleration. Once you know the form of the displacement, then you know the equation of motion for that particular system. So remember, the equation of motion for a simple harmonic system is a cos wt minus phi. So what we need is to get the value of a, which is our amplitude, the value of w, which is angular frequency, and the value of phi, which is our phase phase angle. Okay, so we can get that by using w equals to 2 pi f and making a substitution. We're casting the equation as 2 pi over period, since we have the value of period. So when we make a substitution, we have 2618 rad per seconds, and then we can get our amplitude by using the maximum velocity equation, which is WA, and substituting, we get our amplitude as 2.02 times 10 per minus 3 meter. And then we can use the condition that at equilibrium position, the displacement of the oscillator is actually 0. What that simply means that at equilibrium, there is no displacement. So if we use that fact, that condition, so using that condition, we now substitute when the displacement is 0 into the expression for the displacement, then we should be able to get 0 is equals to a cos wt minus phi equals to 0. So remember, in mathematics, if you have the product of a times b is equals to 0, so it is either a is 0 or b is 0, or even both is 0. But then remember that we have gotten our value for a initially, so a cannot be 0 in this case. So we have cos wt minus phi is definitely equal to 0. So, and the angle that will satisfy that cosine function to be 0 is definitely pi over 2. So that means that we have wt minus phi is equals to pi over 2 rad. So when you do that, if you use the value of the angular frequency in terms of pi rad, which is 833.3 pi rad per second, if you use that and substitute into the expression, we should be able to get our phase angle as 10.16 pi. So when you substitute these values back into the expression for the displacement, we have displacement as a function of time. Thank you so much for watching. Please subscribe for more interesting and insightful videos. Thank you. The House of Shedo.